Have you ever looked at your computer screen and just been, well, amazed at everything it seems to be doing at the same time?
Yeah.
You're probably running, I don't know, a dozen programs, maybe your web browser, some music, that document you're working on, plus all sorts of invisible tasks just humming away in the background.
It really does feel like there are multiple brains, multiple engines inside that box, right? Each dedicated to its own job.
Exactly. How does it pull off that incredible illusion of, simultaneous activity?
It is one of those fundamental achievements of a modern operating system, creating that appearance of many things happening at once, even when, the underlying hardware has a limited number of actual processors.
Absolutely. And that fascinating trick is exactly what we're unpacking in this deep dive right here on InfoSecTube. Today, our mission is to take the sources you've shared with us, your articles, your research notes, your questions, and dive deep into the operating system's primary way of representing a running program.
Yeah, we're focusing on the concept of the process. We'll uncover what a process really is under the hood, explore the surprisingly elegant tools the OS gives your programs to create and manage other processes you've likely heard of: fork, exec, and wait.
Oh yeah, those classics. And we'll also pull back the curtain on the clever low-level mechanisms the OS uses to make all of this multitasking possible securely and efficiently.
And finally, we'll touch on the big question. How does the OS decide which process gets its turn on the CPU when, many are waiting? That's the heart of scheduling.
Right. Our goal for you, the listener, whether you're just starting to explore computer science concepts or you're looking to solidify your understanding of systems, is that by the end of this deep dive, you'll have a much clearer picture of the magic happening inside your machine every time you launch a program.
It really is foundational knowledge.
It unlocks so much about how computers truly work.
Yeah, and understanding this gives you a kind of superpower for debugging, for performance tuning, and just for appreciating the intricate dance happening constantly on your desktop or server.
We're thrilled to be your guides today. And hey, if you find this deep dive valuable, if you have that aha moment we're hoping for, please take a moment to like this video and subscribe to our channel, InfoSecTube. Your support really helps us keep bringing these deep dives to you.
It really does.
Okay, so let's start with that illusion. The core problem is simple, right? You have maybe one, maybe a few physical CPU cores, but you might have dozens, even hundreds of running programs. How does the OS create the sense that each of those programs has its own dedicated processor?
It's exactly like that peach analogy presented in the sources. Imagine you have one physical peach. That's your CPU, but many people who want to eat it.
Okay.
The operating system is the brilliant orchestrator that takes that single physical resource and creates the illusion of many virtual resources, virtual peaches, if you will, one for each program, each eater. The key is sharing that one physical peach so rapidly and seamlessly that the eaters think they each have their own without, stepping on each other's toes.
And the basic technique for that sharing is time sharing.
Right. The OS doesn't let one program run forever. It runs one program for a tiny slice of time, stops it, saves its place, quickly switches to another program, runs that for a slice, stops it, and just cycles through all the programs that are ready to run very quickly.
So it's like those eaters taking incredibly fast, tiny bites, one after another. None of them really get a chance to finish their meal before someone else takes a bite, but they also don't starve.
Exactly.
But here's the trick, right? The real challenge, doing that efficiently and securely while the OS remains in control. The OS is supposed to be the system's guardian. A user program shouldn't be able to just decide to, hog the CPU for an hour.
Or worse.
Or worse, access memory belonging to another program or the OS itself. That would be bad.
Precisely. The OS needs mechanisms not just to share the CPU, but to enforce boundaries and ensure that user programs can't misbehave and, compromise the system.
Which brings us to the central concept we're exploring, the process. What exactly is a process?
At its heart, as the sources define it, a process is simply a running program.
Okay, but what's the difference between the program itself, like the file on disk, and the process?
Think of the program as the recipe, the blueprint. It's a static file sitting on your disk, lifeless instructions.
Right.
The process is the chef following the recipe. It's the dynamic entity that brings the instructions to life. It's not just the code, it's the code plus everything else the program needs to actually execute.
And what makes up that everything else? What's the state associated with a running process?
A few critical things. First and foremost is its memory, specifically its address space. This is where the OS loads the program's code and its data from disk.
Okay.
This memory area is typically structured, with segments for the program's instructions, code, static data, like global variables, the heap for memory you allocate dynamically.
Malloc and stuff.
Yeah, exactly. And the stack for function calls, local variables, return addresses, that kind of thing. Each process generally gets its own private address space.
Okay, memory. What else is part of a process's state?
Well, the contents of the CPU's registers. These are the high-speed storage locations right on the CPU chip that the processor uses constantly as it executes instructions. Things like temporary values, addresses, calculation results.
Super fast memory.
Very fast. When the OS pauses a process, it has to save the values in these registers so they can be restored perfectly when the process resumes.
And there are those really special registers, too.
Yes, absolutely crucial ones, like the program counter, PC. That tells the CPU the memory address of the next instruction to execute. It's how the program progresses.
Can't lose that.
Definitely not. Also, the stack pointer and frame pointer, which manage the process's stack, keeping track of function calls and local data.
And finally, what else defines a process?
I/O information. This includes things like which files the process has open. When a process starts, it typically inherits standard file descriptors for standard input, usually the keyboard, standard output, usually the screen, and standard error, also usually the screen.
So the OS takes the static program file, loads its code and data into a private memory space, sets up the initial registers like the PC to point to the start, sets up those standard file descriptors, and essentially flips a switch, jumping to the program's main function to get it running.
That's the essence of creation, yeah. The sources mention concepts like eager versus lazy loading of memory, which is more about memory virtualization, a topic for maybe another time. But the core idea is giving the program the necessary environment to start executing.
Now, because of time sharing, processes aren't always actively, chewing on the CPU. They exist in different states, right?
Absolutely. Move between states.
What are those basic states?
In a simplified model, you have three key states. First, running. The process is currently executing instructions on a CPU. It's the one with the virtual peach right now.
Got it.
Second, ready. The process is capable of running. It has everything it needs code loaded, data ready. But the OS scheduler has decided to give the CPU to another process for now. It's basically waiting in line for its turn.
Okay, waiting its turn.
And third, blocked. The process is waiting for something external to happen before it can continue. Typically an I/O operation like reading from a disk, waiting for network data to arrive, or even waiting for you to type something. While blocked, it cannot run, even if a CPU is free.
And they transition between these states all the time.
Constantly. A running process might move to ready if its time slice expires or a higher priority process comes along. A ready process moves to running when the scheduler finally picks it. A running process becomes blocked if it, say, requests to read a file. And when that file data is ready, the I/O completion moves the process from blocked back to ready, making it eligible to run again.
The sources even gave us a peek into a real kernel, like by B6, showing a more detailed proc structure with even more states listed there.
Right. More fine-grained states like UNIX-used, before it's even a process, embryo during the creation phase, and the particularly interesting one, zombie.
The undead process. Always sounds cool.
It does, doesn't it? A zombie process has actually finished its execution, it's called exit, but the OS hasn't fully cleaned up all its resources yet. It's lingering.
And why? Why not just get rid of it immediately?
It's a specific design choice, primarily to allow the process's parent process to retrieve its exit status. Did it finish successfully? Did it crash with an error code?
So the parent needs to know what happened.
Exactly. The OS keeps just enough state around like the exit code and the process ID, PID, for the parent to collect this information by calling the wait system call. Once the parent calls wait, the OS knows the information has been collected, it can complete the cleanup, and the zombie process finally disappears for good.
It makes sense that the OS needs, some pretty complex internal data structures to manage all this information for every single process running on the system. There could be hundreds.
Absolutely. This information is typically stored in what's called a process control block, PCB, for each process, or perhaps within a system-wide process list or table. The InfoSecTube proc struct shown in the source provides a concrete example of the kind of data tracked, the PID, the parent's PID, the current state, running, ready, zombie, etc., which files are open, and crucially, the saved CPU context the registers needed for switching.
So that's the what of a process and its life cycle. Now, how do we as programmers actually create and control these processes from within our own programs?
That's where the Process API comes in. Operating systems expose a set of system calls special functions that user programs can invoke to interact with the process management features of the kernel. The sources mention general operations you'd expect: create, destroy, wait, miscellaneous control like suspend resume, and status checks.
But the truly iconic, almost legendary set of calls, especially in the Unix and Linux world, is that trio for process creation and control: fork, exec, and wait.
Yes, and as the source aptly puts it, fork is probably the strangest routine you will ever call.
Why is fork so weird? What makes it strange?
Because when you call fork, it does something unique. It creates a brand new process called the child that is an almost identical copy of the calling process, the parent.
A copy.
Yeah, an almost exact clone. This isn't like launching a new program from scratch. The child inherits copies of the parent's memory space. At least initially, memory sharing gets complicated. It's open files, its current register values, almost everything.
And the wildest part is where the child starts executing, right?
Absolutely critical detail. The child doesn't begin executing at the main function of the program. It begins executing right after the fork call returns, inside the same code as the parent, just picking up from the instruction immediately following fork.
Wait, but if they're running the same code from the same point, how do they know who's who? How does the code differentiate between the parent and the child?
That's the genius, the slightly mind-bending part of the fork. Return value, fork, returns different values to the parent and the child.
Oh.
The parent process receives the process ID, PID, of the newly created child process, a unique positive integer. The child process, however, receives 0, as the return value from fork.
So that's how you do it. You check the return value right after calling fork. Something like, if return code else, I must be the child else. If return code 0, I must be the parent, and return code is my child's PID, else fork failed.
Exactly. The P1.C example in the source demonstrates this beautifully. It prints hello once, then calls fork. Both processes continue from there. One gets a non-zero PID back, the parent. The other gets 0, the child. And they each use that if statement to print a message indicating which process they are, along with their own PID.
And when you run P1.C, you notice that the output hello is always first, but then the parent message and the child message can appear in either order. Sometimes parent first, sometimes child first.
That highlights the non-determinism right after the fork. Once fork returns, both the parent and child are now runnable. They're in the ready state. The OS scheduler gets to decide which one gets the CPU first, and you have no guarantee about that ordering without adding some kind of synchronization mechanism.
Okay, so fork creates the nearly identical copy. What if the parent needs to pause its own work until the child process it just created is completely finished?
That's the job of the wait system call.
Yeah.
Or sometimes wait, which offers more specific control. A parent process calls wait, and the OS blocks the parent's execution.
Puts it to sleep, essentially.
Right, puts it into the block state until one of its child processes terminates, exits, or is killed.
The P2.C example in the source code adds a call to wait, NULL, in the parent's execution path after the fork.
Right, and if you run P2.C, the output is deterministic. You'll see the hello message, then the child's message always prints first, then the child exits, and only then does the parent's final message print.
How does that work?
The parent might get scheduled right after the fork, but when its code reaches the wait NULL call, the OS stops the parent and puts it in the block state. It stays blocked until the child process finishes executing and exits. At that point, the OS wakes up the parent, moves it back to ready, wait, returns to the parent, and the parent can then proceed to print its final message.
So wait, is how parents synchronize with their children's completion? Makes sense. Now, for the third part of this famous trio.exec.
If fork is about making a copy of the same program, exec, is how a process completely transforms itself to run a different program.
The P3.C example shows this. The parent forks, and then the child process calls execvp to run the standard WC word count utility on the P3.C source file itself.
Precisely. After the fork, the child process determines it's the child, because fork returns 0, sets up the arguments for WC, like the program name WC and the file name P3.C, and then calls execvp WC, myargs.
And the output we see is hello from before the fork. Then the child prints its child message. Then suddenly we see the output from the WC command, the lines, words, characters count. And then finally the parent prints its parent message because it waited. The child's original code just stops after the execv call.
That's because of what exec fundamentally does. It tells the OS, Okay, load the code and static data for this new program, like WC, from its executable file on disk and overwrite my current memory space with it.
Overwrite. So the original program's code is just gone.
Gone. Replaced entirely by the new program's code and data segments. The heap and stack are effectively wiped and reinitialized for the new program.
So exec doesn't create a new process ID or anything. It just transforms the current process.
Exactly. It's a transformation, not a creation. It
Yeah.
reuses the existing process. And here's another strange property, kind of the flip side of fork's double return.
Mm-hmm.
A successful call to exec never returns to the calling code.
It never returns.
Think about it. If exec succeeds, the OS has replaced the calling program's code with the new program's code. There's no calling code to return to anymore. The process simply starts executing the entry point, main, usually, of the new program. The line of code immediately following a successful exec call is, by definition, unreachable.
Wow. Okay. So if exec does return, it means something went wrong.
Exactly. If exec fails, maybe the program you specified doesn't exist or you don't have permission to run it, then it will return an error code to the original program, which can then print an error message or try something else.
That's why the print, this should not print, line after execbp and p3.c is truly unreachable code. The source also notes there's a whole family of exec calls, not just execvp.
Yes, there's execl, execv, execl, and so on. They mostly differ in how you pass the program name and its command line arguments, as a list of strings directly in the call, as an array of strings, whether the OS should search the system's path environment variable to find the executable, etc.
Lots of options.
Lots of options. And as the source strongly recommends, and we absolutely echo, the best way to understand the nuances is to read the manual pages for these calls on your system, RTFM. Read the fine manual. It's where the definitive details live for system calls.
Definitely good advice. So we have fork, which copies the current process, exec, which transforms the current process into a new program, and wait, which lets a parent pause until a child finishes. It still feels a bit roundabout, maybe. To separate the act of creating a process fork from the act of running a new program in it, exec. Why this specific, slightly strange combination?
This separation is arguably the single most powerful and flexible design decision in the entire UNIX process API. It seems odd at first, but it's absolutely essential for building fundamental tools like the command line shell.
Ah, the shell, the thing we type commands into all day.
Right. Think about what the shell does. It's just a user program itself. It showed you a prompt. You type a command, maybe lsl. The shell needs to find the bindle's executable and run it with the argument L. Now, the shell can't just call exec bindles directly within its own process, because then the shell program itself would be gone, replaced by else. You'd run one command and your shell would disappear.
That wouldn't be very useful.
Not at all. So what does the shell do? It calls fork first. This creates a child process that's an exact copy of the shell. Then in that child process, it calls exec to load and run bindles. Meanwhile, back in the original parent shell process, it typically calls wait to pause itself until the child process finishes. Once the child completes, wait returns in the parent shell and can then print a new prompt ready for your next command.
Okay, so the separation allows the shell to create a new isolated environment, first using fork, and then load the specific command the user requested into that environment using exec.
Exactly. And the true genius, the core insight enabled by this separation, is the ability for the shell, or any parent process, to run code in the child process after the fork call returns, but before the exec call happens.
Oh, there's a window there.
A critical window of opportunity. This allows the shell to meticulously set up the child's environment, precisely how the user requested, before the new program starts executing.
Like setting up where the input comes from or where the output goes?
The perfect example, input-output redirection. Think about typing wcp3.c output.txt in your shell.
Okay, count words in p3.c, send the result to output.txt.
Right. When the shell processes this, it first forks a child. Now, in that child process, before it calls exec to run the WC program, the shell executes some setup code. This code calls the close system call to close file descriptor 1, which normally points to the screen standard output. Then it calls the open system call to open the file output.txt for writing.
And open reuses the file descriptor number.
By convention, open returns the lowest available file descriptor number. Since descriptor 1 was just closed, open output.txt will typically return 1. So now file descriptor 1 in the child process points to the file output.txt instead of the screen.
The p4.c example in the sources illustrates this exact sequence: close one, then open the new file.
It does. And crucially, The OS ensures that file descriptors remain open across an exec call. So after the shell has done this redirection setup in the child, it calls exec to run WC. When the WC program starts running, it doesn't know anything about redirection. It just writes its results to standard output, file descriptor 1, as it normally would. But because the shell cleverly rewired file descriptor 1 to point to output.txt before calling exec, the output magically goes to the file instead of the screen, totally transparent to the WC program itself.
That's incredibly elegant and powerful. And pipes, like in grep file WCSL, work on a similar principle, using that gap between fork and exec.
Yes, very similar. Pipes connect the standard output of one process directly to the standard input of another using a special buffer managed by the kernel. You type that command, the shell uses the pipe system call first to create this kernel buffer and get 2 file descriptors, one for writing, one for reading. Then it forks twice to create 2 children.
Okay, 2 children.
In the first child, for grep, before execing grep, the shell closes its standard output and uses dub2 to make file descriptor 1 point to the right end of the pipe. In the second child, for WC, before execing WC, it closes its standard input and uses dub2 to make file descriptor 0 point to the read end of the pipe.
Wow.
Then it execs grep in the first child and WC in the second. The output of grep flows directly into the input of WC through the kernel's pipe buffer. Again, that window between fork and exec is absolutely essential for setting up these sophisticated communication channels before the actual commands start running.
So this initially strange-seeming trio of fork, exec, and wait is actually a cornerstone of flexible system design and the power we take for granted on the command line.
Absolutely. It's a fantastic example of how a few simple orthogonal primitives can be combined to enable incredibly complex and powerful functionality.
Yeah.
It's really quite beautiful design.
Beyond that core trio, the sources briefly mention a couple of other ways the OS allows programs and users to interact with processes. Signals, for instance.
Right. Signals are a kind of software interrupt, a way for the OS or other processes to send a notification to a specific process. You can use the kill system call to send a signal.
Like when I hit Ctrl+C in my terminal?
Exactly. Your terminal emulator typically sends a SIGINT interrupt signal to the foreground process running in the shell, which usually tells that process to terminate cleanly. Pressing Ctrl+Z often sends SIGJATSP, telling the process to stop execution.
Can programs react to signals?
Yes, programs can use the signal or SIG action system calls to register signal handlers functions that should be run when a specific signal arrives. This allows them to intercept signals and perhaps clean up resources before exiting, or ignore certain signals, or handle SIGTSTP by saving state before pausing.
But I probably can't just send a SIG-kill signal to, say, a critical system process owned by somebody else, right?
Generally, no. And this brings up the crucial concept of users and security in the OS. Operating systems enforce permissions. Typically, a user can only send signals to or otherwise control processes that they own, processes running under their user ID. This prevents ordinary users, or potentially malicious programs, from killing system demons or interfering with processes belonging to other users logged into the system.
Unless you are the superuser, the all-powerful root.
Ah, yes, root, the one user count that operates outside many of these standard restrictions. Root typically has unrestricted privileges. It can send signals to any process, access any file on the system regardless of permissions, perform highly privileged operations like loading kernel modules, mounting file systems, or shutting down the entire machine.
So with great power.
Doors out comes great responsibility. Exactly. As the sources mentioned, quoting that idea which traces back further but was popularized elsewhere, using root privileges should always be done with extreme care and only when absolutely necessary, because a mistake made as root can have catastrophic consequences for the entire system.
Good warning. And finally, the sources point to some useful command line tools that leverage these underlying OS features for process monitoring and management, things we can actually use day to day.
Yeah, absolutely essential tools for anyone managing or even just curious about a UNIX-like system. Tools like BS, process status, to list the processes currently running, see their PIDs, states, CPU usage, memory usage, etc.
Top is another popular one.
Top, or HTOP, which gives you a dynamic, real-time view of running processes sorted by CPU usage or memory, constantly updating. Very handy for seeing what's currently active.
And if you need to actually stop a process,
you can use the kill command, giving it the PID of the process you want to signal. By default, it sends sigterm for a graceful shutdown, but you can specify others like sigkill for a forceful termination. Or kill-al, which lets you send a signal to all processes matching a given name.
These are invaluable for just inspecting what's happening on your system, and again, the advice stands.
Read the man pages. RTFM. They'll tell you all the options and details for X, top, kill, and all the other system utilities. Graphical tools like Activity Monitor on Mac OS or Task Manager on Windows provide similar views, of course.
Okay. We've covered what a process is, its life cycle, and how programs use system calls like fork, exec, wait, and kill to interact with them. Now let's dive deeper into the how behind the magic. How does the OS actually run a program directly on the CPU, but then somehow wrestle control back to switch to another one, all while maintaining security?
This is the core implementation technique, often referred to as limited direct execution, LDE.
Okay, direct execution sounds simple enough. The OS just runs the program's code directly on the physical CPU hardware.
That's the starting point, and it's absolutely key for performance. You want user programs to run as fast as possible, which means running their instructions natively on the processor. The OS sets up the process's state, loads its code into memory, sets up its registers, etc., and then simply jumps to the program's starting instruction.
Like the simple protocol shown conceptually in Figure 6.1 in the sources. OS sets up, runs program finishes, and returns control, OS cleans up. Very straightforward.
Right. It's fast because there's minimal OS overhead while the program is just calculating or manipulating its own data.
But the technique is called limited direct execution. What are the limitations and why are they absolutely necessary?
The limitations are all about maintaining control and ensuring security. There are two major problems the OS faces if it just lets user programs run completely free without any constraints. Problem 1. Restricted operations. User programs inevitably need to do things that affect system resources or hardware perform I/O operations, like reading a file or sending network packets, allocate more memory from the system, create other processes using fork. If user programs could execute the raw hardware instructions for these operations directly, there would be zero security or control. A malicious program could directly access the disk controller to read any file, overwrite critical OS data structures in memory, access devices it shouldn't, or simply allocate all system memory for itself. Chaos.
So how does the OS allow user programs to request these necessary privileged operations safely?
This is solved with crucial hardware support, hardware modes or privilege levels. Modern CPUs can operate in at least two distinct modes. There's user mode, which is a restricted unprivileged mode where normal user applications run, and there's kernel mode, also called supervisor mode or privileged mode, where the trusted OS kernel runs. Only code running in kernel mode has access to the full range of hardware instructions, can manipulate device registers directly, control memory management hardware, and manage process switching.
Okay, so user programs run in the less powerful user mode. How do they ask the kernel, running in the powerful kernel mode, to do something privileged for them, like open a file?
They do this through system calls. When a user program needs the OS to perform a privileged operation, it doesn't try to execute the privileged instruction itself. The hardware would likely trap that as an error anyway. Instead, it executes a special, non-privileged hardware instruction, often called a trap instruction, or sometimes syscall or sysenter on different architectures.
What does that trap instruction actually do at the hardware level?
It's designed specifically as a controlled, secure entry point into the kernel. When the CPU executes a trap instruction, the hardware automatically performs several actions. First, it usually saves the current state of the user program, at minimum the program counter, so it knows where to return, and some key registers, often onto a special stack reserved for the kernel. Crucially, it then switches the CPU's operating mode from user mode to kernel mode, elevating its privilege level. Finally, it looks up a predefined address in a special table and forces execution to jump to that specific controlled entry point within the OS kernel code, the trap handler routine.
And the user program can't just tell the trap instruction to jump to any random address inside the kernel. That sounds dangerous.
Absolutely not. That would be a massive security vulnerability. The OS kernel sets up a trap table, or interrupt vector table, during the system boot process, an operation that itself requires kernel privileges. This table essentially maps different trap reasons, like system call number X, divide by zero error, timer interrupted, to the specific memory addresses of the kernel's handler routines for those events. The hardware consults this table, which user programs cannot modify, to determine exactly where in the trusted kernel code to jump.
So when my C code calls fork, underneath the hood, the C library wrapper function likely puts the specific number identifying the fork system call into a designated register, then executes the trap instruction. The hardware saves my state, switches to kernel mode, looks up the handler address for that system call number in the trap table, and jumps there.
Precisely. The kernel's generic system call trap handler then reads the system call number passed by the user code, validates it. Is this a real system call number? Possibly validates the arguments passed in other registers, and then dispatches control to the specific internal kernel function that implements fork. This use of system call numbers and the hardware-managed trap table provide layers of protection.
And once the kernel finishes doing the work for the system call, like creating the child process for fork, how does it get back to my user program?
It uses a corresponding special hardware instruction, often called something like return from trap or IRET sexit. This instruction does the reverse of the trap. It restores the user program's saved state, registers, program counter, from where the hardware or kernel saved it. It switches the CPU's mode back from kernel mode to user mode, lowering its privilege level again, and then it resumes execution in the user program at the instruction immediately following the original trap instruction.
So that whole cycle user program runs hit syscall, traps to kernel mode, kernel handler runs, kernel returns, return from trap back to user program continues. That's the core loop of limited direct execution shown conceptually in figure 6.2.
That's the fundamental mechanism. And a critical, non-negotiable part of the kernel's job during that system call handler phase is to carefully validate any arguments passed from user space before using them. For example, if a user program calls write and passes a pointer to a buffer and a memory address, the kernel must rigorously check. Is that buffer pointer actually within the user program's legitimate address space? Is the length valid? It cannot just trust the user program, because a malicious program could pass a pointer to kernel memory, trying to trick the kernel into overwriting its own data.
That makes sense. Constant vigilance from the kernel.
Always.
Quick aside, and just to reinforce, why do these system calls like read or write look just like normal C function calls in my source code if they involve all this hardware trapping?
That's the convenience provided by the standard C library. Other the food. When you call read in your C code, you're not directly executing the trap instruction. You're calling a small wrapper function provided by lib. That wrapper function contains the necessary architecture-specific assembly code to load the system call number for read into the correct register, put the arguments, file descriptor, buffer pointer length into other agreed-upon registers or stack locations, execute the actual trap instruction, check the return value from the kernel for errors, and then return that result back to your C code, making it look like a simple function call. It abstracts away the low-level hardware interaction.
Got it. Okay, so hardware modes and traps solve problem 1, allowing privileged operations safely. But what about problem 2, regaining control from a runaway process? What if a user program is just, I don't know, calculating digits of pi in a tight loop? It's not making any system calls, so it's not trapping into the kernel voluntarily. How does the OS ever get the CPU back to switch to another process that might be waiting?
This is where the limited in LDE becomes absolutely essential for multitasking. If the user process is just looping infinitely in user mode, executing only non-privileged instructions, the OS itself isn't running, and it has no inherent way to regain control based only on the system call mechanism.
In older, maybe simpler operating systems, wasn't there something called cooperative scheduling?
Yeah.
Where they just hoped programs would behave?
Yes, exactly. Early or simpler systems often relied on processes to be well-behaved and voluntarily give up the CPU periodically. They either had to make system calls fairly often, which implicitly yields control, or they were expected to explicitly call a special yield system call just to say, okay, OS, I'm done for now, let someone else run.
What's the problem with that? Seems trusting.
The huge problem is, what if a process has a bug, like an accidental infinite loop? Or what if it's intentionally malicious and never calls yield or makes a system call? It would just run forever, monopolizing the CPU. The OS would never regain control, other waiting processes would starve, and the entire system would likely hang, requiring a manual reboot. Not a robust design for any kind of multi-user or reliable multitasking system.
Definitely not. So how do modern, robust operating systems like Linux, Windows, Mac OS solve this? How do they force control back from a potentially uncooperative process?
With hardware assistance again, the key is the timer interrupt. The OS, during boot, a privileged operation, programs a hardware timer chip on the motherboard to generate an interrupt signal after a fixed recurring interval, maybe every few milliseconds, maybe every 10 or 100 milliseconds, depending on the OS configuration. This timer runs independently of the CPU.
And when the timer goes off, it generates an interrupt.
Exactly. It sends a signal to the CPU.
Right.
The hardware reacts to this timer interrupt very similarly to how it reacts to a system call trap. It forcefully halts the currently running user process, regardless of what instruction it was executing. It saves the user process's essential state, program counter, registers, onto its kernel stack. It switches the CPU into kernel mode, and it forces execution to jump to a predefined timer interrupt handler routine within the OS kernel. The address for this handler was also set up by the OS in the trap table during boot.
Brilliant. So the OS is absolutely guaranteed to get control back periodically, no matter what the user program is doing, even if it's stuck in an infinite loop doing nothing but math.
Precisely. The timer interrupt is the OS's ultimate safety net. It ensures that no single user process can monopolize the CPU indefinitely in a preemptive multitasking system. It guarantees the OS scheduler gets a chance to run periodically and decide if the current process should continue, or if another ready process should get the CPU next.
And if the OS does decide to switch from the process that was just running, either because its time slice ended due to a timer interrupt, or maybe it blocked itself by making a system call like read, to a different ready process, that actual transition mechanism is called a context switch.
Yes, a context switch is the low-level nuts and bolts procedure the OS uses to stop executing one process and start executing another one that's already in the ready state.
What actually happens step by step during that switch inside the kernel?
Okay, so the OS has decided process A should stop for now and process B should run. The kernel's context switching code needs to perform two main tasks. First, it must save the complete execution context of the outgoing process, process A. This includes all its general-purpose CPU registers, its floating-point registers, its program counter, which points to where it was interrupted, and importantly, its kernel stack pointer. This entire state is saved into process A's process control block, PCB, structure stored in kernel memory.
Okay, saved A's state, now what?
Second, the OS needs to load the previously saved context of the incoming process, process B, from process B's PCB. This involves restoring all of B's saved registers, its saved program counter, and switching the CPU's active kernel stack pointer to point to B's kernel stack. Finally, the OS executes that special return from trap instruction we talked about. But crucially, this instruction now uses the just restored state of process B. So instead of returning to where process A left off, the return from trap effectively makes the CPU jump to the instruction where process B was last interrupted, restoring its registers and switching back to user mode if B was interrupted in user mode. Process B seamlessly resumes execution as if it had never been stopped.
So the return from trap is kind of the final step that actually makes the switch happen from the CPU's perspective, using the state loaded by the OS's context switch routine.
It's exactly. Figure 6.3 in the sources provides a nice conceptual diagram of this flow. Process A, running 90's timer interrupt. Hardware saves A's user state, traps to kernel. 90's kernel runs the timer handler. That OS scheduler decides to run. BOS calls its internal switch. Routine. OS software saves A's kernel state, like its kernel stack pointer, loads B's kernel state, effectively switching the kernel context. OS executes return from trap using B's saved user state. Hardware restores B's user registers SBC, switches to user mode, jumps to B's last instruction, and poof, B is now running.
There are kind of two levels of saving restoring then. Hardware handles user registers during the trap return from trap, and OS software handles kernel register stack during the explicit context switch call within the kernel. That's
a good way to think about it, yes. The details vary by architecture, but that separation of concerns is common. The source even provides a little peek at the by-v6 kernel's assembly code for its routine, figure 6.4, showing you how low-level this operation really is, manually pushing and popping specific registers onto and off the kernel stack to save and restore the kernel context. It really gives you an appreciation for what's happening down there, it really does. And while these steps happen very, very quickly measured in microseconds or even nanoseconds on modern hardware, context switches are not free. They have a cost.
What's the cost?
There's the direct cost of executing the instructions to save and restore all those registers. But often, a more significant indirect cost comes from the impact on the CPU's memory hierarchy. When you switch processes, the data and instructions belonging to the old process that were recently used, and therefore likely sitting in the CPU's fast caches, L1, L2, L3, are suddenly useless to the new process.
So the new process starts with cold caches.
Right. Exactly. It will likely experience a burst of cache misses as it starts running, needing to fetch its own data and instructions from slower main memory. Similarly, the translation look-aside buffer, TLB, which caches virtual to physical address translations, might need to be flushed or will contain stale entries, slowing down memory accesses initially. Tools like ElmBench, mentioned in the sources, can actually measure the aggregate cost of a context switch on your specific system, including these cache effects.
So minimizing unnecessary context switches is generally good for performance.
Generally, yes, though it's a trade-off against responsiveness, as we'll see with scheduling. And the sources hint at further complexities, like handling interrupts that occur during an interrupt handler or context switch, and the need for locking mechanisms when multiple processes or interrupt handlers access shared kernel data structures concurrently. But those are deeper topics.
Okay, so the combined power of hardware support modes, traps, timer interrupts, and careful OS software trap handlers, context switching routines, PCB management allows the OS to implement this limited direct execution. It gives programs the speed of running directly on the CPU, but retains the OS's ability to interrupt them, switch between them fairly, and enforce security boundaries.
It's the foundational magic, the core mechanism, that enables the illusion of multiple virtual CPUs and seamless multitasking that we started with.
Right. Now that we understand the mechanisms that how the OS uses to run and switch processes, the next big piece of the puzzle is the policy. How does the OS decide which runnable process from the ready queue it should choose to run at any given moment?
That's the domain of the scheduler, sometimes called the dispatcher. Designing a good scheduling policy is really tricky because it depends heavily on what you want to optimize for, maybe minimizing average waiting time, maybe maximizing throughput, maybe ensuring fairness, maybe guaranteeing quick response times for interactive tasks.
Yeah.
And the best policy often depends on the characteristics of the jobs being run.
The sources wisely start by making some very unrealistic, simplifying assumptions about the jobs, just to make the basic concepts clear before getting real.
Right. Assumptions like, all jobs run for the same amount of time. They all arrive at the exact same moment. Once started, they run to completion without interruption, no preemption. They only use the CPU, no I/O. And the most unrealistic of all, the OS somehow magically knows exactly how long each job will take to run in advance.
The Oracle OS.
Pretty much. We know these aren't true in the real world, but they allow us to analyze some simple scheduling policies in isolation first, before we start relaxing those assumptions one by one.
And to compare these different policies, we need some metrics. What are we measuring? The primary metric discussed initially is turnaround time.
Right. Turnaround time for a job is simply the total time it spends in the system. The time it finishes minus the time it arrived. Peak completion interval. If all jobs happen to arrive at time 0, then it's just the completion time. It's a measure of total time elapsed from submission to completion.
Okay, turnaround time. What else?
Another important consideration is fairness. Does the scheduler give different processes a reasonably fair share of the CPU over time? There are formal metrics like Jane's Fairness Index, but often there's a common trade-off. Policies that are really good at optimizing performance metrics like average turnaround time might end up being quite unfair to certain types of jobs, and vice versa. It's a classic tension in system design.
Okay, let's look at the first, simplest policy under those initial crazy assumptions. FIFO, or first in, first out, also known as first come, first served, FCFS.
The simplest possible approach. Jobs are run in the strict order they arrive in the ready queue. If you have 3 jobs, A, B, and C, each taking exactly 10 seconds to run, and they all arrive magically at time 0, FIFO runs A first, it finishes at T10, then B finishes at T20, then C finishes at T30. The average turnaround time is 10 plus 20 plus 30, 3 equals 20 seconds. Figure 7.1 in the source material shows this simple timeline. It's straightforward and works okay if all jobs are roughly the same length.
But the problems start immediately when job lengths vary significantly.
Right.
You get the convoy effect.
A major drawback of pure FIFO. Take the example from the sources. Job A is long, it takes 100 seconds. Jobs B and C are short, they only take 10 seconds each. But they all arrive at time 0. FIFO, sticking to arrival order, runs the long job A first. A runs for 100 seconds. During that entire time, the short jobs B and C just sit there, idle in the ready queue, waiting.
Ouch.
Then, after A finally finishes at T100, B runs, finishing at T110, then C runs, finishing at T120. The average turnaround time is now 100 plus 110 plus 120, 3 equals 110 seconds. Figure 7.2 visualizes this disaster clearly. The 2 short jobs got stuck behind one long job, and their turnaround times ballooned massively.
Yeah, that's like getting stuck behind someone buying lottery tickets for the whole office when you just wanted a pack of gum at the only open checkout lane.
So how do we fix this convoy effect, at least in the simple case where all jobs arrive at the same time? That leads directly to the next policy. Shortest job first, SJF. Given that all jobs arrive simultaneously and we have our magic oracle telling us how long each will run, the provably optimal approach for minimizing average turnaround time is intuitive. Simply run the job with the shortest execution duration first, then the next shortest, and so on.
So using that same A100, B10, C10 example, all arriving at T0 with SJF. The scheduler looks at the runtimes, it sees B and C are shortest, 10s each, and A is longest, 100s. It picks one of the short ones, say B, runs and finishes at T10. Then it picks the other short one, C runs from T10 to T20. Finally, only the long job, A, remains. A runs from T20 to T120.
Now look at the turnaround times. B finished at 10, C at 20, A at 120. The average turnaround is 10 plus 20 plus 120, 3 equal than 50, 3 equals 50 seconds. Much, much better than FIFO's 110 seconds for this workload. Figure 7.3 shows this much more efficient schedule. SJF avoids letting short jobs get stuck behind long ones as long as they all start together.
Okay, SJF is provably optimal for average turnaround if all jobs arrive at the same time and we know their lengths. But what happens when we relax that simultaneous arrival assumption? What if the long job A, 100s, arrives first at T0, but the short jobs B10s and C10s arrive just a little bit later, say at T10?
Now we need to consider if our SJF scheduler is preemptive or non-preemptive. If it's non-preemptive, meaning once a job starts, it runs until it either finishes completely or blocks itself for I/O, then even though shorter jobs arrive later, they can't interrupt the currently running job.
So in that example, A100 at T0, B10 at T10, C10 at T10, with non-preemptive SJF. A starts at T0. At T10, B and C arrive and are ready. The scheduler might notice they are shorter than A's remaining time, but because it's non-preemptive, A just keeps running and running until it finally finishes at T100.
Right. Only then, at T100, can the scheduler run B, finishes at 1 to 10, and then C finishes at 120. The average turnaround is still high. Average 0 is plus 110 to 10, plus 1 to 10, 3 equals 100 plus 110, 3 equals 310, 3, roughly 103 seconds. Figure 7.4 illustrates this. The lead arriving short jobs still form a convoy behind the long job that happened to arrive first.
So just knowing which job is shortest isn't enough if you let a long job keep the CPU when a shorter one becomes ready. You need to be able to interrupt it.
Correct. This is where we relax the run-to-completion assumption and introduce preemption, the ability for the OS scheduler, usually triggered by an event like a timer interrupt or a new job arrival, to forcibly stop the currently running job, saving a state, and switch to a different ready job. Adding preemption to the SJF logic gives us what's often called STCF, shortest time to completion first, or sometimes PSJF, preemptive shortest job first. The policy is refined. Whenever a scheduling decision needs to be made, against a new job arrives, or the currently running job finishes or blocks, the scheduler examines all jobs currently in the ready state, considers how much execution time each one has remaining, and schedules the job with the least remaining time.
Let's retry our example. A100 at T0, B10 at T10, C10 at T10. With preemptive STCF, A starts running at T0, it runs for 10 seconds. At T10, B and C arrive. The timer interrupt might fire around then, or the arrival event triggers the scheduler. The scheduler looks at the ready jobs. A has 90 seconds remaining, B has 10 seconds remaining, C has 10 seconds remaining.
The shortest remaining time is 10 seconds, held by both B and C. STCF preempts A, pauses it, saves its state, and schedules one of the shorter jobs, say B. B runs for its full 10 seconds, finishing at T20. When B finishes, the scheduler runs again. The ready jobs are now A, still 90s left, and C 10s left.
Shortest remaining is C.
Right. So STCF schedules C. C runs for its 10 seconds, finishing at T30. When C finishes, the schedule runs again. The only job left in the ready queue is A, with 90 seconds remaining. STCF schedules A, resumes execution from where it was preempted, and runs until it finally completes at T, but 30 plus 90 equals 120.
So the overall schedule is A runs 0-10, then B runs 10-20, then C runs 20-30, then A runs 31-20. Figure 7.5 shows this interleaved execution.
Now let's look at turnaround times. A finished at 120, arrived 0 minus 120. B finished at 20, arrived 10, minus 10. C finished at 30, arrived 10, minus 20. The average turnaround is 120 plus 10 plus 20. 3 equals 153 equals 50 seconds. Much better. STCF with preemption handles late arrivals very efficiently by always prioritizing the job closest to finishing. In fact, STCF is provably optimal for average turnaround time, given that we know the job run times.
Okay, so STCF, or preemptive SJF, is the champion for minimizing average turnaround time. But you mentioned earlier, turnaround time isn't the only thing people care about, especially in interactive systems like my desktop PC or a web server handling user requests.
Exactly. If you type a command or click an icon, you don't just care when the task finishes, you care when it starts doing something, when you get some feedback. Waiting 10 seconds just to see a window appear is frustrating.
So we need a different metric.
That leads us to a crucial new metric, response time. It's defined as the time from when a job arrives in the system until the first time it gets to run on the CPU. T first run arrival. It measures initial responsiveness.
And policies like SJF or STCF, which focus purely on completion time, can actually be quite bad for response time, can't they?
They could be terrible for it. Imagine 3 equally short interactive jobs. A, B, C each needs 5 seconds of CPU time, all arrive at T-gal. Under SJF or STCF, since they arrive together, A starts immediately, response time 0. B has to wait until A finishes at T5, response time 5. C has to wait until both A and B finish at T10, response time 10. Figure 7.6 in the source shows this. The average response time here is 0 plus 5 plus 10, 3 equals 5 seconds. Waiting 5 or 10 seconds just to start seeing something happen feels incredibly sluggish for an interactive task.
Yeah, that's unacceptable for a modern UI. So optimizing only for turnaround using STCF isn't the answer for interactive systems. We need a policy that specifically aims to give every job a little bit of CPU time quickly, even if it means making them all take longer to finish overall.
That's precisely the philosophy behind the round-robin scheduling policy, sometimes just called time slicing. Instead of running a job until it finishes, like SJF, or until a shorter job arrives, like STCF, RR runs each job for, at most, a small fixed duration called a time slice, or scheduling quantum.
Okay.
When a job starts running, the OS sets the timer interrupt for the end of the time slice, say 10 or 100 milliseconds. If the job is still running when the timer interrupt occurs, the OS preempts it, puts it at the end of the ready queue, and picks the next job from the front of the ready queue to run for its time slice. It just cycles through all the ready jobs, giving each a small turn.
Let's try our 3 short interactive jobs, A, B, C, 5s each, arrive T0, with round robin, maybe using a 1-second time slice. What happens?
Okay, T0. A runs for 1 euro. Timer fires. A is preempted, still needs 4s, put at the back of the queue.
Yeah.
P, C, A.
T1, B runs for 1s. Timer fires. B preempted, needs 4s, put it back. Q, C, A, B.
T2. C runs for 1, C fires. C preempted, needs 4s, put it back. Q, A, B, C.
T3. A runs for 1s, now needs 3s, preempted, Q, B, C, A, and so on. They just keep cycling. Figure 7.7 illustrates this interleaving.
Now, let's look at the response times. A started running at T or at response time 0. B got its first turn at T1, response time 1. C got its first turn at T2, response time 2. The average response time is 0 plus 1 plus 2, 3 equals 1 second. Much, much better than SJF's average of 5 seconds for these jobs. The system feels more responsive because every job gets attention quickly.
The length of that time slice seems really critical for how round robin behaves. What's the trade-off there?
It's the key tuning parameter and involves a fundamental trade-off, as you say. A shorter time slice leads to better response times. Every job gets its first turn faster, and interactive tasks feel snappier. However, shorter slices mean more frequent context switches.
And we know context switches have overhead.
Right. Each context switch consumes CPU time just for the OS to save and restore state, manage queues, etc., time that could have been used for running user code. If the time slice is too short, say comparable to the context switch cost itself, the system might spend almost all its time just switching between jobs and get very little actual work done. You're amortizing the fixed context switch cost over a smaller and smaller amount of productive work.
So what about a longer time slice?
A longer time slice reduces the relative overhead of context switching. More useful work gets done between switches, but it increases response times. In the limit, if the time slice becomes longer than the longest job, round robin essentially degenerates back into FIFO.
So the OS designer has to pick a time slice length that balances good responsiveness against acceptable system efficiency and overhead, maybe tens or hundreds of milliseconds.
Typically in that range, yes. It's a classic engineering trade-off with no single perfect answer for all workloads.
Okay, so round robin is great for response time because it's fair and gives everyone a turn quickly, but what's the cost? What does it sacrifice?
Round robin is generally quite bad for average turnaround time, especially compared to SJF or STCF. Because it forces all jobs, even short ones, to wait for all other jobs to take their turns repeatedly, it stretches out the total execution time for everyone.
Let's look at our A, B, C, 5s each, one slice example again. When do they actually finish under RR?
A runs at T0, 3, 6, 9, 12, total 5s, finishing at T13. B runs at T1, 4, 7, 10, total 5s, finishing at T14. C runs at T2, 5, 8, 11, 14, total 5s, finishing at T15. The average turnaround time is 13 plus 14 plus 15, 3 equals 42, 3 equals 14 seconds.
Wow, 14 seconds average turnaround. Whereas non-preemptive SJF for those same jobs arriving at T0 would finish them at T5, T10, T15 for an average turnaround of 5 plus 10 plus 15, 3 plus 10 seconds. RR made them take significantly longer overall, even though it felt more responsive initially.
It really highlights a fundamental trade-off. SJFS TCF optimize for turnaround time. getting jobs completed efficiently overall, but can starve short jobs for responsiveness if a long job is running. Round-robin optimizes for response time, getting every job started quickly through fair sharing, but generally leads to worse overall turnaround time because it stretches everything out.
Yeah.
You usually can't have the best of both worlds simultaneously with these simple policies.
Okay, let's add another layer of realism back in. We relax the run-to-completion assumption with preemption. We relax simultaneous arrivals. Now let's relax the CPU-only assumption. Real programs perform I/O. They read files, write to the network, wait for the user.
Indeed, and this behavior is critical for scheduling. When a program needs to perform an I/O operation, like read from disk, it typically makes a system call. The OS initiates the operation with the hardware device, like the disk controller, and then crucially puts the process into the blocked state. Because the process usually can't continue executing until the I/O operation completes, and I/O operations can take a relatively long time, milliseconds, or even longer, compared to nanosecond CPU instructions. While the process is blocked waiting for I/O, it's not using the CPU. This is a perfect opportunity for the OS scheduler to pick another process from the ready queue and run it on the CPU.
So I/O allows for natural context switches. And when the I/O operation finally finishes, IOG, the disk controller signals data, is ready.
The hardware generates an interrupt. The RS's interrupt handler runs, figures out which process was waiting for this I/O, gathers the results, like the data read from disk, and moves that process from the blocked state back to the ready state, making it eligible to be scheduled for CPU time again.
How do modern schedulers typically leverage this I/O behavior? Do they treat the whole program as one unit, or?
They tend to view a process's execution not as one long monolithic run, but as an alternating sequence of CPU bursts, periods where the process is running instructions on the CPU, and I/O waits, periods where the process is blocked waiting for I/O. The scheduler can then potentially make decisions based on the characteristics of these individual CPU bursts.
The examples in the source, figures 7.8 and 7.9, show a clear difference here. Figure 7.8 depicts a scenario with two processes. A does a short CPU burst, then a long I/O wait, then another short CPU burst. B just does one long CPU burst. A naive scheduler might run A's first burst, then when A blocks for I/O, it runs B, but then the CPU might sit idle while A is still doing I/O even after B finishes.
Well, that's inefficient. But a scheduler that's aware of I/O and maybe tries to estimate the length of the next CPU burst for each ready process can schedule much more effectively, achieving overlap. Overlap between CPU computation and I/O waiting. As shown conceptually in figure 7.9, the scheduler might run A's first short CPU burst. When A blocks for I/O, the scheduler immediately switches to B. B runs on the CPU while A's I/O operation is happening in parallel in the disk controller. When A's I/O finishes, A becomes ready again with its next short CPU burst. If the scheduler, perhaps using STCF logic applied to estimated burst times, thinks A's next burst is shorter than B's remaining time, it might even preempt B, run A's second burst, let A block for its next I/O, and then resume B.
So by switching intelligently when processes block for I/O, the scheduler can keep the CPU busy more often and allow I/O devices to work in parallel, improving overall system throughput and utilization.
Exactly. And it also tends to make interactive programs, which typically have a pattern of short CPU bursts followed by waiting for user input or network response, feel much snappier because their short CPU bursts get scheduled quickly between the longer bursts of CPU-bound jobs. Treating the CPU burst rather than the whole job as the entity to be scheduled is key.
Okay, we've relaxed assumptions about arrival times, run to completion with preemption, and CPU-only jobs by incorporating I/O. But the biggest, ugliest, most unrealistic assumption still remains from the start. The OS generally doesn't know in advance how long a job will run in total, or even how long its next CPU burst will be. It doesn't have that magic crystal ball.
This is the fundamental Oracle problem in scheduling. Without knowing the future runtimes or burst lengths, implementing pure SJF or STCF, which rely on knowing those lengths, is impossible in a real system. How can you schedule the shortest job, or the one with the shortest time to completion, if you don't know those times?
So the big question is, how can a real-world scheduler try to approximate the good properties of these theoretical policies? How can it try to achieve low turnaround time, like STCF, for long batch jobs, and low response time, like RR, for short interactive jobs, without having perfect knowledge of the future?
That is the central challenge that drives the design of more complex, practical schedulers used in modern operating systems. And it's where they have to start employing heuristics, essentially, making educated guesses, often based on observing the past behavior of a process to predict its future behavior.
Using the past to predict the future.
In a way, yes. For example, if a process has consistently been using only short CPU bursts before blocking for I/O, the scheduler might assume its next CPU burst will also be short and give it higher priority, like STCF would. If another process has been running for long periods without blocking, the scheduler might assume it's CPU bound and give it lower priority, but maybe a longer time slice, treating more like a batch job where turnaround is more important than instant response. This hints at more advanced policies like the multi-level feedback queue, MLFQ, which the sources mentioned briefly.
Multi-level feedback queue sounds complicated.
It is a bit more involved, yes. MLFQ uses multiple queues, typically with different priority levels. New jobs might start in a high-priority queue with a short time slice, aiming for good response time like RR. If a job uses its full time slice, it gets demoted to a lower priority queue, perhaps with a longer time slice. If a job blocks for I/O before its time slice is up, it might stay at a high priority level or even get promoted back up when the I/O completes, under the assumption it's an interactive job. The scheduler always picks a job from the highest priority non-empty queue to run.
So it's a dynamic system that tries to automatically classify jobs as interactive or batch based on their behavior and adjust their priority and time slice accordingly.
That's the core idea, yes.
Right.
It tries to learn and adapt to the workload without requiring that impossible oracle. Designing and tuning MLFQ schedulers is complex, with lots of parameters to consider: how many queues, what are the time slices, how do jobs move between queues. But it's a very common approach in real-world systems because it tries to balance those competing goals of turnaround and response time reasonably well for mixed workloads.
It sounds like a fascinating area where theory meets a lot of practical heuristics and tuning. Definitely a puzzle worth exploring further, maybe in a future deep dive. All right, we have covered a significant amount of ground today. Wow. We've investigated that initial illusion of multitasking, defined the core process abstraction with its machine state and lifecycle states, running, ready, blocked, zombie. We dove deep into that crucial UNIX process, API, trio fork, exec, and wait and saw how their separation enables the power of shells, redirection, and pipes.
Yeah, that separation is key.
We explored the underlying limited direct execution mechanisms, the need for hardware modes, user versus kernel, the role of system calls and traps for controlled entry into the kernel, the absolute necessity of the timer interrupt for preemptive multitasking, and the mechanics of the context switch.
The nuts and bolts that make it all work safely and efficiently.
And then we examined the basic scheduling policies, FIFO and its convoy effect, SJF, FSTCF, and their optimality for turnaround, if you have an oracle, round robin and its focus on response time, and the inherent trade-offs between these goals. Plus, how I/O interaction changes the game.
It's truly amazing when you step back and see how the OS layers all these concepts and mechanisms together. Process abstraction, APIs, LDE, scheduling to create that seamless experience of virtual CPUs and running many things at once.
Understanding these fundamental building blocks isn't just, academic trivia. If you're writing software, if you're trying to figure out why your system is slow, if you're concerned about security, knowing how processes work, how they're managed, how they're scheduled, it's absolutely key.
It provides the essential context for almost everything else you'll learn about how real computer systems function, from applications down to the hardware. It's foundational.
We really hope this deep dive has been valuable for you, our listeners, here on InfoSecTube. We aim to give you a comprehensive look at these core OS concepts, explaining them clearly whether you're a beginner or looking to refresh your expert knowledge.
And we hope we've sparked your curiosity to learn even more. Thank you for joining us on this exploration.
And hey, if you did find this discussion helpful, if you had some of those aha moments along the way, please show us some love. Click that like button and definitely subscribe to our channel, InfoSecTube. Your support really does help us keep creating detailed deep dives like this one.
It absolutely encourages us to keep digging deep into these fascinating, fundamental topics of computer science.
Now, as we wrap up, let's just circle back to that final puzzle we touched upon. The OS needs to schedule all these processes, trying to balance competing goals like finishing jobs quickly, turnaround, while also making interactive tasks feel responsive. But it has to do this without knowing for sure how long any given job will run or what its next action will be.
It's like trying to manage that peach eating scenario again.
Yeah.
But now the eaters arrive at random times. They take bites of completely unpredictable sizes, and they might pause randomly to, check their phone or get a drink. You have no idea when they'll start eating again. How do you decide who gets the next bite to keep everyone reasonably happy?
How does the OS make the best possible decision about who gets the CPU next when it's essentially flying blind about the future needs and behaviors of each process? That fundamental uncertainty, that lack of an oracle, is what drives the design of all those more complex, heuristic-based, real-world scheduling policies like MLFQ.
And it's a challenge that OS developers and systems researchers are still constantly refining and adapting as workloads and hardware evolve.
A truly fascinating problem and perhaps a great place to leave things for today.